are all the way down to the input layer. Now the network is random. It's garbage. So you would think, because the model changed in such a dramatic way, prediction, now explanation, should also change. But it doesn't. And you might argue, well, technically these two pictures look different. But remember, the final consumer of your interpretability method are humans. And as a human, I don't know if I will draw a completely different conclusion looking at these two pictures. The second model was random prediction. So it was terrible model. Yes. Random learned weights. So these two pictures deliver a similar message. The belly of the bird seems important in both pictures. So is the cheek of the bird. So is this really the evidence of prediction? Well, this test makes me doubt that conclusion. Here's the full results. We're randomizing just the logit layer in a cascading fashion all the way down to the input layer. So on the rightmost column, you're looking at completely random network. This is, you didn't train any of these networks. And yet, you can see some methods visually don't change at all, even in complete randomization. Now, interesting thing is that the gradient, the vanilla gradient, the top row, which a lot of these methods are based on, seems to be the best bet. Shocked by these results, we did another experiment where this time we trained the network with random labels. So neural network is happily fitting these random labels without really learning what it means to be digit 0. But it seems to deliver similar messages to the network that did learn what 0 means. And again, our discovery, vanilla gradient seems to be the best bet here as well. So what does that mean to us? Well, I think it's going back to something pretty fundamental about how we evaluate interpretability methods. These methods thought to work because when we show it to humans, it made sense. They liked what they were looking at. It's a classical confirmation bias. So what do we do about this? Well, I think we need to ensure inserting some sanity checks whenever you develop an interpretable method. And for example, you can craft an experiment I'm going to talk about where we know the ground truth and show that at least in that simple case, your interpretability method can match that ground truth. And this is I think this is a good science, but kind of annoying science. Because at the end of the day, you have more questions than answers. We don't know what these first order gradients or these methods are really picking up. And some of these methods said that it improved human tasks, like actual medical tasks. So we want to understand, we need to do more study to figure out why that was the case and what these maps are really showing. But what it does give us is a wish list. What would you do differently if you can build a new model, new interpretable method? So saliency map gives you a number per pixel from which I draw this map, but there are too many numbers for you to look at. So at the end of the day, what you do is you look at this map and subjectively judge, oh yeah, the eye part seems to be brighter, belly seems to be brighter. So final evaluation is human subjective judgment. It used input features as a language of explanation. And maybe that works for human layperson who doesn't really know computer science, but really layperson doesn't even know that computers process pictures in pixels. Because humans don't process pictures with pixels. And this is giving local understanding, which means you need a picture or one particular data point to explain. It's not really about all the junco bird, it's just about this picture, this junco bird. So if we were to do something different, maybe we need something more quantitative. Maybe we should rule out that subjectivity in evaluation. And maybe we should use something other than pixels, something that is intuitive to humans, high-level concepts. I never say to you, look at this pixel 2.3, value number 0.5, isn't it beautiful? I never say that. I say, oh, look at this bird, has a white belly, it's kind of cute, right? High-level concepts. And maybe that will help the explanation being available for layperson, people who don't really know computer science or machine learning, or any degree for that matter. What else do we want? Well, local understanding is important. Oh, I'll keep stepping on this. Local understanding is important, but sometimes we just want to get a general idea of what this model can do globally. What is the evidence for generally for Junko bird class, not just this one picture. So the second part is about doing that, developing that interpretability method. It's called the testing with concept activation vectors. So here the problem is the same. This time, instead of bird, I'm going to use cache machine. Problem is you have the network, you get a picture, network predicts something, what's in the picture, and your goal is to answer why was this a cache machine. Now let's use this saliency map that we just talked about to help us answer what do we really want to ask. So as I stare at this beautiful picture, I notice that there's this human in front of a cache machine that's kind of bright. So I start to wonder, well, maybe the fact that human was in the picture mattered. Maybe the human concept mattered. As I stare more, I notice this cartwheel behind the human is bright. Maybe for some weird reason, wheel was an important concept in predicting cache machine. If these concepts did matter and existed in the model, then I would like to know which one of these concepts did and how much, relatively, which one was more important. And was this true for all other cache machine predictions or just this one picture? Problem is that you can't really express this concept in pixels, especially if you want to do it across many pictures. Now, you would have been able to answer this question if your input feature was human and wheels. Well, you didn't. I just made up these concepts. And the whole point is to answer the question, why was this cache machine, without having to retrain the model. So wouldn't it be great if we can get quantitative importance measure of the concept that you just came up with using the concepts that users chose? So that's what we did. This is testing with concept activation vector. And the goal is to find you a quantitative measure of how important concept, like gender or race, is for the prediction, even if that concept was not there when you're training the model. So let me be a little more concrete. Let's say you have a model that gets a picture and predicts if there's a doctor in this picture or not. I'm curious whether the gender concept was important in this picture. So TCAP is like a microscope that gets attached to the model when it needs access to the activations and outputs a number per concept. So in this case, not woman seems to be more important than being a woman. And depending on what you're trying to do, this may not be something you want. And it does that if and only if the network learned about this concept. If humans give a concept that network never learned about, then it's going to say, oh, I don't know this concept. Sorry, I can't answer this question for you. So throughout the talk, I'm going to use this example. So forget about the cache machine. I'm going to use zebra. And our question now is, I have a zebra classifier, and I want to know how important the stripeness concept was in this classification. So first, you say, well, okay, concept sounds like a good idea, but what do you even mean by concept? Like, how do you express concept? Well, we do the simplest possible thing. We express concept as a vector. And it's really simple, and we gave it a name. The name is concept activation vector. And to learn this vector, it's pretty simple. You need a couple of ingredients. First, you need examples of concepts. So in this case, some pictures of stripes. And you need some random images. Then you need your network that you want to investigate, and the function, activation function, that maps the input image to the activation of a layer. So you have this, you pipe in these images into the network, and you collect activations of the concept and the random. Then you simply just train a linear classifier that separates concept activations from random activations. Then you find the vector that is orthogonal to the decision boundary, and that's your cap. So what is this cap? Well, it simply really points from the random concept activations to more like the concept activations. That's all there is. And this idea is not new. It has been studied many times and used in many literature. If you remember the initial word2vec paper, they learned this gender vector by subtracting a bunch of men words and woman words. Similar idea, we just decide to train a linear classifier, but you can also do that too. So cool, we have this vector. Now, how is this vector is gonna help us to find that quantitative concept importance that I talked about, or the TCAP score? It's also super simple. The way you find that is simply doing a type of very simple sensitivity test. What does that mean? You take the probability of zebra, the logic layer, 1 neuron, and you take directional derivative with the vector that you just learned. So what does that mean? Well, it just means that if I change this activation to be more like that concept or less like the concept, how much should the probability of zebra swings? If it swings a lot, it's an important concept. If it doesn't, it's not an important concept. That's it. Now, local explanations are proven to be very sensitive, so we do this for many, many zebra pictures. So we get that directional derivative for many, many zebra pictures, and simply the final TCAP score is a number between 0 and 1. And what is this number? It's simply the ratio of zebra pictures that outputted positive directional derivative. So let's say you have 100 zebra pictures. How many of them was sensitive to changing the stripeness concept? And that is your final TCAP score. Now, this is the simplest possible thing you can do, but I've seen people extending this to regression and like flipping the inequality to incorporate some more sophisticated final TCAP scores. So cool, that's really the whole technical part. Really simple, pretty genetic. It's so genetic that it's not limited to just images. It's been, in fact, since this work is out, applied to sequence models and text data and other things. There's one more step though, the CAV validation. Why? Well, this CAV thing, the vector that we learned, lives in a high dimensional space. And we all know in this audience in particular that high dimensional is sort of flaky. We don't quite know, like there might be adversarial examples. We really need to be sure that this vector really means did not return high sensitivity by chance. There are lots of ways to test this, but here's one way to test this. So remember, we learned this vector by training linear classifier to separate concept activations from random activations. These are random pictures, so you can put any sets of random pictures, as many as you can, from which you will get many, many CAVs, and each CAV for this particular class of interest will get me many, many TCAP scores. Now you have many, many TCAP scores for the same concept, for the same class. And you can view that as samples from a distribution, and if it nicely agrees to that, oh yes, stripe is important for zebra, you might see something nice like Gaussian there. Then we compare that to TCAV score distributions from random CAV. So CAVs trained with random images and random images. And only if it passes the statistical significant testing that these two distributions are very different, then only then we use this concept to provide an explanation. So that's the whole technical part. You learn the vector, you take the directional derivative, and you just do this CAV with statistical testing, and you're done. So let's look at some cool results. So first experiment is my favorite. This is the one that sanity check experiment where you can craft an experiment where you know the ground truth, and we're going to show that this method can match. Question is this. So here's the setup. What we did is we took an image, just ImageNet image, and I wrote caption on the left bottom corner. So this picture has a cab, so I wrote CAB. What am I doing? Why am I doing this? Well, by doing this, I'm introducing two concepts artificially that I have a complete control over. The classifier can use images to do the classification, or the caption to do the classification. Now then I trained, made 4 different training data sets with different noise in the caption. What does that mean? 30% noisy means that 30% of the time I wrote something random, like tiger, just to encourage the network to do slightly different things. And then, once the networks are trained, all of which achieve high performance, it's a pretty easy task, I gave an image without the caption and see how well it does. Now, if the image concept was important, it used images, then it's going to do pretty well. If it didn't, it's not going to do pretty well. And that could be used as a proxy ground truth for image concept. Any questions so far? Okay, cool. So with that, and it matched. So cap class, interestingly, cap class, none of the network ever cared for captions. It always looked at the image. Cucumber class, oh yeah, you know that because the accuracy blue line up here, and you want that to match with green, at least the pattern-wise it wants to match, and it matches. Cucumber class was slightly different. It went crazy on the caption if I gave a perfect caption. And the trend changed as I increased the noise in the caption. This blue line is the accuracy. Looks pretty high, but we have 3 classes, so 33% is random, it's pretty low. So that's cool, but maybe this experiment is just so simple that saliency map can do the same thing. So let's have a look. So here I'm showing you 4 different saliency map methods, one of which is my own work. And I'm showing you, I passed an image with a caption and got saliency maps. So remember, the cap class never cared about the caption. It only looked at the image. However, a lot of saliency maps are showing where the caption is highlighted. It seems to think that it's important. So that is not good, but you might ask, well, Bean, maybe you cherry pick this example. Maybe. So we did a Turker experiment. We asked 50 Turkers to tell us how, given these 4 images and according the saliency maps, tell us which concept was more important. Was it the image or was it the concept for 3 classes? So the result is super interesting. So there are 2 concepts. So the random is 50. Humans can do 52%. It's basically random. They can't tell. And oftentimes, Turkers are split in half. Half of the Turkers said, oh yeah, it's definitely images. And half of the Turkers were like, oh, it's definitely captions. And more interestingly, they're so confident when you're wrong. And this is something that I see over and over again in my experiments, confirmation bias. They liked what they saw, and they're confident. 40% of people who answered incorrectly or correctly answered that I am as confident as I will ever be. And this is something that hints us that these methods, when you're presenting to human, you have to be extra careful and aware of human limitations, human's feature, maybe not a bug, to ensure that these methods are used properly. So we got excited after this. We applied to a famous image classification network and tested a set of different concepts. We tested color, we tested race, and objects. Now the fire engine, the red comes out high. Green is high because a lot of fire engines were sitting on the grassy field. And then this would make sense to you if you're from an area where fire engines are red. In fact, a lot of areas in the world, this is taken from Canberra, Australia, fire engines are not red, they're yellow. There's actually a really good reason why they should be yellow. So it's showing some geographical bias. Some other work, previous work had conjectured that a certain race matters in predicting certain classes, and now we can quantitatively verify, yeah, that's true. If you remember the very first Deep Dream blog post, they discovered in classifying dumbbell, they discovered this neuron that looks like an arm, muscular arm. And that was conjecture, oh, maybe the arm matters in predicting dumbbell. And it turns out, yes, it is. And for this one, I didn't have arms picture, so I went to Google image search and literally collected 33 arms images, and it passed the statistical testing and everything. Let me please stop stepping on this. All right, so what this is showing is going back to our goal that this method might help you to decide whether your model reflects the values that we care. So last, we got really excited and I'll take you to the doctors. Diabetic retinopathy is a treatable but sight-threatening condition. And so the brain medical team has developed this model that has high accuracy, 85%. And our question was, well, that's great, but is this model using the same diagnostic concepts that human doctors would have used? So we went to a doctor and asked her, what kind of concepts would you look for more severe level of DR? By the way, this is a picture of retina. It's like a back of your eyeball. And what kind of concepts do you not expect to see for this level? And we did the same thing for other levels. And then we collected this concept, asked TCAV, what do you think? And here's the results. When the model had high accuracy, in this case, DR level 4, this is most the severe level of DR, model seems to have used the same set of concepts that doctors would have used. So that's good. Now, the story was slightly different when the model had mediocre performance. Level 1, it turns out that it was also using this HMA feature. It's like a blown up vessel in your eye, like a fat vessel. And apparently, model was using HMA as one of the important concepts. And later, we dig further and found out that level 1 was often confused with level 2, so next serious level of DR, and level 2 had a lot of HMA. So it was reflecting how it was confused between these two classes. So going back to our original goal, this method might help you to decide whether your model is reflecting your domain expert knowledge or not, so that you can decide when is the right time to use this model, or perhaps when you shouldn't. So the summary, we talked about TCAV. It is a method that uses high-level concept instead of input feature or pixel-based explanation, and that concepts come from your users, doctors, experts, whatever language that makes sense to them. And this method can output a quantitative one number per concept, only if and only if that concept was learned in the network. Last but not least, I'm going to talk about an interpretability method that can help you decide not to use machine learning model because you can't trust the prediction. It's called trust score. Any questions before I go farther? Okay, cool. So problem here is find when you should or should not trust the prediction. And in particular, goal is to get high precision on probably correct predictions and probably incorrect predictions. What does that mean? It's a precision. It's not recall, not accuracy, but precision. So if you give me 10 data points, I want as many true positives there as possible. Okay? And remember, if I'm going for accuracy, it's equivalent to training just a better classifier. And you can simplify this problem by just learning what we call a trust score. It's just a better measure of confidence score by the model. And you can do this on top of a model. Now this method is so simple that I can explain to you in one slide. We define a trust score, and imagine you have one-dimensional data. So there are lots of x's living in this one-dimensional world, and I plot the density of these data points. So there's a little bump there, and there's a second bump there, and maybe this first bump is class A, first class, second bump is class B. Now I want to know whether this prediction of this data point, this red star right here, if I can trust that prediction or not. And this red star is predicted as class A. Then you just need two distances. First distance is you find your closest friend who was also predicted as class A, and then you find another friend closest data point that was predicted to in any other class. So one guy in your class, one guy in another class, and then you calculate the ratio, and that's it. That's your trust score. We do one more thing. If your data has a lot of outliers, we want to filter them out to be a little bit more aware of them, and we use dbScan to do that. And of course, you can use this calculate this distance using input images, but we find it better to do it on activations. It's pretty obvious sometimes you can do that. So when we first did this, we did this for many UCI data set, and we were like, that can't be true. It works so well. It's beating the model confidence out of the water. So it's either the model confidence is really bad or something magical about this score. So we tried a lot, although it does, the performance does deteriorate as you increase the number of features, so you can't really have it all yet. But for a lot of other data sets, it worked so well. So then we built different combinations of these two distances, like subtract them, normalize them, and do some other fancy thing. But none of them beat the simplest thing. We also built a separate model. Its only job is to predict which one is going to be trustworthy and not trustworthy. It also didn't do as well as this ratio. So why was that? Well, it turns out that this particular ratio is revealing some signal from base optimal classifier. And we prove in our paper that this is true for when data point is living in the input space that's kind of big, or if the data point is living in some other low-dimensional manifold, and that manifold has some noise in it. This is all true, and we can show this with high probability. So apparently that was why. So today I talked about 3 interpretability methods, and checking for interpretability method. First, we talked about this family of methods that perhaps we need to rethink about what they're showing and how we use them, sanity checks for saliency maps. And then I talked about TCAP, testing with concept activation vectors, an interpretability method that uses high-level concepts so the layperson can use and leverage this powerful tool called machine learning. And finally, I talked about a really simple way to estimate whether you can trust your prediction or not using trust score. So with that, that is all. Thank you.